तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we introduced the concept of microprogrammed design of controller for ASM. Any digital system can be partitioned into architecture or a functional part and the controller part. We had seen how to draw ASM, algorithmic state machine chart for the controller. In many earlier lectures, we had seen how to implement the ASM using several techniques like gate based design, multiplexer based design, prompt based design and PLA based design, programmable logic array based design, programmable array logic based, programmable logic array or programmable array logic based design. In the last lecture, we introduced the concept of microprogrammed implementation with two advantages. One is a little flexibility in changing hardware versus programmability. In a hardware design, once you make a design, if you make changes, you may have to redo the design. A programmable approach is good, so that way a ROM based approach is very good. But the problem with the ROM based approach is the size of the ROM becomes very large when the system becomes large. With the number of states increasing and the number of inputs increasing, the size of the ROM increases exponentially. On the other hand, we saw in the last lecture in a microprogrammed approach, which is also similar to a ROM based design. We do not give the ROM table or the microprogram table as we give in the conventional sense, where for each state give the input conditions for all the available inputs, the conditions of all the available inputs. We only select such of those inputs which are going to affect the transition from the given state to the next state. So that means we are not going to give the table, the ROM table or the program table involving all the inputs. We will only select those inputs which are going to affect the immediate transition. And we saw that this, as the size of the design increases, the increase in the design and the hardware size of the ROM is only linear, not exponential. It makes a lot of difference in terms of hardware. Not only this hardware cost, which is not very much today, RAM cost is not very much, but the tediousness, the tedium by which with which you have to write the RAM table, to generate the RAM table, that becomes extremely cumbersome if the number of states are very large and the number of inputs are very large. And we took an example of a simple ASM and saw how to implement it using a programmable microprogram based approach, where we saw for each state we will test one of the inputs, sometimes no input is tested, and decide if the input tested is true, what happens to the controller, which state does it go to. If the input is false, which state does it go to, we decide and make a table. In that approach we saw that for each state we test one qualifier, sometimes 0 qualifier, no qualifier also has to be given as a qualifier test, no qualifier. We have to give a true address and the false address, that is the next state when the qualifier is true, next state when the qualifier is false. We said we could do one more improvement in this design by not indicating both the false address and true address for a qualifier test. We will only give one of these two states, the other state will be an increment of the existing state. So, at any given state, let us say 0 0 0, we will test a qualifier and the qualifier is true for one of the conditions of qualifier, either true or false, we will make the next state as 0 0 1. And for other state, other test, the result of the qualifier being different, then instead of going to 0 0 1, it will go to some other state. So, which means I do not have to keep writing the next state, which is an increment of the present state. So, I can drop that from my table, and to that extent I can shrink the size of the RAM. So, in that, this is where we stopped in the last lecture. So, we will take the same example of the ASM that we took as an example for in the last lecture, where there are only 4 states S0, S1, S2, S3, 2 qualifiers P and Q, and 3 outputs ABC. The only change I have made, in fact we did it in the last lecture itself, the assignment of the states, earlier I had taken arbitrary assignment, I had called it 0, 1, 2, 3 corresponding to S0, S1, S2, S3, now I have made a slight change in this. Today I am calling this state 0 0 state, this 0 1 state, this 1 0 state, this 1 1 state. Why did I do it? Because whenever the qualifier is tested, one of the next states should be an increment or of the present state. For example, if you are in a circuit is in state S0, P is tested, either S1 or S2 to which it goes, one of them should be next state to 1 0. So, this 1 0, this 1 1. So, S2 happens to be next state S0, binary next state. When I say next state, in a binary sequence. Likewise, the other qualifier tested here is Q. In condition S3, in state S3 we test qualifier Q, it can be false or true. If it is false, it goes back to 0 1. There is no way I can make this 0 1 next state of 0 1 because this has to go back to this state. That means the next state when the qualifier is true from S3 to S0, this has to be increment of this. So, if this 0 1, this has to be necessarily to be 1 0, because this cannot be 0 1 goes back to 0 1. So, there is no question of this being the increment of this state, whereas the other path, this state can be increment of this state. So, whenever there is a qualifier tested from a given state, make one of the next states as a binary increment of the present state. The other state can be anything, and if there is no qualifier tested, this condition does not apply. So, to that extent I have to make some changes in the ASM, which I have done. So, now I can rewrite the table, microprogram table, the present address, qualifier index, and next state is only 1 now. The other next state is automatically increment. So, I do not have to write 2 columns, I do not have to write 2 sets of next states, and then the output. Making use of the same type of definitions as yesterday, as in the last lecture, the qualifier index, there are only 2 qualifiers, P and Q. The last lecture we called P is 0, Q is 1. So, whenever there is no qualifier, we use one of them. When you make this, it is not possible, because here I need an extra qualifier saying no qualifier. So, I need to have one more index, so no qualifier. So, this means I am going to make it 0 0 no qualifier, 0 1 is P, 1 0 is Q. This no qualifier condition was not required in the previous implementation, because I can always make one of those qualifiers as the qualifier tested even when there is no qualifier to be tested, and make both the true address and false address same. That way I do not have to worry about the no qualifier case, but here I have to worry about it. So, I have to put the qualifier index as 0, 1 or 2. Output we already decided, output code, no output is 0 0 0, output A is 0 1, output B is 1 0, output C is 1 1. This is the same as what we did in the last lecture, and I purposely left a blank here, if you have observed that. So, I like to know when a test is done, qualifier test is done, the next state is given here, whether that state will go if the qualifier is true, or that state will go if the qualifier is false. I need to know whether the next state given, next address given by this table is a true address next state or a false address next state. So, that means I will have to put a true or false bit. So, now I will put the present state 0 1 0 0 0 1 1 0 1 1. In 0 0 state, no qualifier is tested. When no qualifier is tested, the next address has to be 1 0. Output in this state is B, which is 1 0. I will come to this bit in a minute. This is 0 1. Qualifier tested is Q, and now we have to see 1 more than 0 1 is 1 0. I do not have to write it. What I have to write is what is not the incremental value, which is 0 1 again. Output in this state is C, which is 1 1. 1 0 state A, state S0, qualifier tested is P, which is 0 1. 1 0 goes to 1 1, I do not have to write it. 1 0 goes to 0 0, I have to write it because this is a non incremental value. So, 1 0 to 0 0. Finally, F 1 1, qualifier tested is no qualifier tested, and next state is 0 1. Output is nothing. Question is, what do I write here? If it is true, does it go to this state? If it is false, does it go to this state? That I have to write here. It goes to this state whether it is true or false. For example, take the qualifier tested 1 1 0 0 1, you take this state P. In this state, if this goes to 0 1, if this goes to 0 0, 0 1 goes to 1 0, if the qualifier is true, we do not have to write it. It goes back to 0 1, the qualifier is false. So, I have to write here false. Likewise, when I am testing this condition in 1 0 state, qualifier tested is P, which is 0 1. If it is true, it goes to 0 0, which is a non-incremental value of this. If it's false, it goes to 1 1, it is an incremental value. So, I do not have to write this, I have to write this false, which is true, which is 1. I have to write 1 here. And what do I write these two places? Doesn't, it's a true value. True value will write here. So, because this is anyway it is a non-incremental value. So, this is what I have to implement. So, my logic is going to be very simple. I am going to have a microprogrammed ROM whose address comes from the present address, because the output code will be there, you do not have to worry about this. Two bits for output code. Earlier I had a true address coming and false address coming, one of them was selected using a multiplexer. Now I do not have to do that, I will have only the qualifier index. The qualifier index which is n plus 1, if n is the number of inputs, actually it is total number of inputs, logarithmic value of that. So, there are 2 bits actually it is, because qualifier index is only 3, qualifier index is only 2 bits, even though there are 2 plus 1 3 qualifiers, no qualifier this and this, we are going to use 2 bits, and this goes to a multiplexer whose very first value is always true, that is no qualifier, because whenever we go to the no qualifier we have put a true as this thing here. Whenever there is no qualifier we have true, and that is the new value to be added. The new value is a true value. So, I need a true for the first one, rest of them will be the actual qualifiers, namely P and Q. So, this is a mux. Now, I have this here counter here, I have a counter which will give you the next address, which is 2 bits, which is what will go here. This completes my, and this counter will produce either a new value or an incremental value. If it is a present state, is the next state is an incremental value of the present state variable, it has to add 1, or if it is a new value, it has to load a new value. So, the counter will have the feature called load and count, load. What is loaded? The value given by the next address. What is incremented? You do not need the present address plus 1. Present address plus 1 is the next address, so I do not have to load it, I only count it. Loading will be this called next address, in this case again 2 bits. Next address gets loaded or it is counted. How will you decide that? That will be decided based on the bit being true or false. That means I need to have a comparator. I need to have a exclusive NOR gate, wherein I take this value from the multiplexer and compare it with this value, which is the true false bit. if true false bit is, in each case we have to decide whether false is going to give the loading or true is going to give the loading, and accordingly do this. So, this true false bit along with this will be compared by an exclusive NOR gate, and that will be given to load, and inverted will be given to count. For example, take the first row, no qualifier, true false bit is 1, no qualifier, this is 1. So, no qualifier is index is 0 0. So, when 0 0 index is presented here, this is 1. So, 1 comes here, true false bit is 1 from the table. So, 1 and 1 compared, output is a 1, then exclusive NOR gate, not exclusive OR gate. So, 1 will load the next address, which is this. On the other hand, let us take this, I get the 0 1, the qualifier index is 1 0, which is the this one Q, and when Q is false, if the true false bit is 0, I need to load it, because true false bit is 0, I need to load this value. True false bit is true, I do not have to load, it will add. So, if the true false bit is 0, this will be a 0 and this is a 0, 0 0 equal, I load it. On the other hand, if the true false bit is 1, this is 0 always. If Q is 1, if it is 1 and this is 0, this is 0, so this will increment and it will count. So, it will increment by 1 or it will load a new value. So, this is as architecture. Yesterday we drew the architecture, the last lecture we drew the architecture for the single address, single qualifier, double address, true address and false address. So, we have now reduced, in this case of course you do not see the reduction very much, because we have taken a very trivial example of 4 states. So, 2 address, 1 address was here, 1 address was there. In the last implementation we had this, this is same as this, output is code is same, next address is 2 bits. We had 2 of these, 1 row is complete, 1 column is completely removed. Instead we have an extra column of true false bit, and the qualifier index, unfortunately there are only 2 qualifiers 0 and 1. Single qualifier double address case, we need a qualifier address 0 or 1. Now, I have increased 1 bit for the qualifier index and 1 bit for this, so I have not had any saving. But imagine the number of states are very large. Supposing we had a 5 qualifiers instead of 6 qualifiers, earlier were 5 qualifiers, 5 qualifiers would have required 3 bits. Now, extra qualifier index being 0 0 0 will not add any more bit. So, the number of bits increase is not there. 1 extra bit will be there for true false bit, but address bit, if the next address is several bits long, I will increase 1 bit for true false bit, but save on 1 address. It looks trivial example because I do not see any appreciable change in the size of the ROM. The reason is there are only 4 states, 2 address lines will be, 2 address bits are required to represent 4 states, out of which 1 has to go for true false bit, and this particular example happens to be also 1 more bit has been added to the qualifier index. Because of this, suppose there is no bit added to the qualifier index, supposing the qualifier index was 6 earlier and now it is 7, no problem. And suppose the number of bits for the next address is several bits, then we have saved. Adding 1 extra bit for true false, we will save knockoff entire address. To that extent, I can shrink the size of the programmable ROM. So, basically we have now given you a tool by which an elegant implementation. ASM is a must in any controller. Any digital system requires a controller, architectural controller. Controller is best represented by ASM, and ASM can be implemented any way you like. You can use gates, you can use multiplexers, etc. These are all hardwired examples. No change possible, especially gate gate based no change is possible, multiplexer based we can make some more change, some slight changes. PROM based some sort of programmability is there, but as I said PROM based is a cumbersome procedure because the size of the PROM becomes very large, system is very large, as well as the table, writing the ROM table becomes a tedious affair. So, this microprogram approach takes the essence of the PROM based approach and simplifies in the hardware sense, so gives you an elegant method. And there are two types in which we will only in each of these we will we draw the ASM with one qualifier to be tested, either the 0 qualifier is also considered as one qualifier because no qualifier, only one qualifier tested in each. Two addresses will be given, true address and false address, or we can give only one address and assume the next to be the increment of the previous address. These are the two options. One is called single qualifier double address, that is what we did in the last lecture. What we see today is called single address, single qualifier. With this background, let us go back to an example, revisit an example we have done. We have done several examples in our previous lectures, and one of very interesting and somewhat extensive examples is was a dice controller. If you remember, we had a dice game. Let me remove this so I can show you the ASM of the dice game. I wanted to revisit the dice game controller design using the ASM approach, using PIL we have done, programmable array logic, in one of the earlier lectures. Instead of spending again a lot of time trying to explain the problem, I request you to go back and look at the problem definition, the specifications, the architectural requirements and the ASM of that. The same ASM has been redrawn here for implementing as a microcontroller, microprogram based approach implementation. What do you mean by redrawing? We have already done the ASM for implementation. Redrawing is necessary for the following reason: we can only test one qualifier at a time. In one given state, I can only test one qualifier or one input. Input is same as the qualifier. Earlier, many examples I have seen something like this. Something like this is an accepted ASM. We know how to draw the next state table for this, or the ASM table that they call it. You can draw the ASM table for it and implement it using multiplexers, using ROM, whatever. But this is not allowed for a microprogram approach. In a microprogram approach, I need to have only one qualifier. For example, I cannot have two qualifiers tested in this state. This is okay, but if it is false, you should go to another state. Only then the next address can be true address or false address. Next address has to be either a true address or a false address. So, that is what I mean by redrawing. The controller of the ASM or the controller for the dice game has been redrawn, keeping in mind I can only test one qualifier at a time in a given state. Second change I have made is I have eliminated all conditional outputs. In this state, if this is false and this is false, this is the output, and then this goes to this state. So, this can be state 1, this can be state 2, this can be state 3, this can be state 4. In state 1, if this is false and this is false, this output is generated and then it goes to state 3 or whatever. That conditional output has no place in a microprogram approach. So, all conditional output boxes have to be replaced by output boxes. So, in effect we are increasing the number of states. We are increasing the number of states for two reasons. One is to introduce states between qualifiers. If a series of qualifiers is tested in a given state, we have to introduce an extra state in between, and whenever there is a conditional output, I need to introduce an extra state. So, I may have to introduce a few additional states, but remember, number of state increases is not going to increase the number of variables. Variable increase is going to be logarithm to base 2 of the number of states. Supposing we are having a 10 state example, I need 4 state variables. I can add another 6 states without changing the size of my ROM. Even if I go to 17 or 18 states, all I need to do is an extra state, only one extra variable. I am not changing the number of qualifiers. Number of qualifiers is what is giving you the enormous size of the ROM. Why are we getting enormous size of the ROM in a ROM implementation? The exponential power of the number of qualifiers. The size of the ROM is determined by 2 power the number of state variables plus the number of qualifiers. Here the number of qualifiers is completely dropped from the ROM size, it only comes as a width, as a qualifier index. So, by adding a few states extra, you are not going to increase the size enormously. So, with that in mind, I am not going to go through this example, since we have already done this enough, considered in great detail all aspects of this game. I can show you a couple of places where the state has been increased now. For example, we had, what is the, in this state 4, these are the state variables. I have given binary decimal numbers to make the life simple. From state number 4 to state number 5, there is a qualifier tested, dice greater than 9, dice is greater than or equal to 9, we will have to see whether true or false. And this goes to y, where I have to again test whether dice is less than or equal to 4. So, this dice greater than or equal to 9 or less than or equal to 4, that is a case, that means the dice value is between 4 and 9. I could have put 2 qualifiers one after the other. I cannot do that now. I introduced the extra state 5. 5 has no value, 5 has no, is a dummy state. This state has been introduced just to separate this qualifier from this qualifier. This is one example of how to introduce extra state. Likewise, introduce extra state in the case of the earlier figure we had this clear score register was a conditional output. Now, I have to make it as a regular out state. The conditional output box has been taken as a state, and in which the output is clear score register is signal is generated. I have not changed the names of the signals, either the names of the qualifiers, names of signals. ASM in principle is the same. Changes have been made. I request you to go over this state ASM along with the previous ASM and see what are the changes I have made. Functionally, there is no change, no variable has been introduced, no variable has been deleted either as a qualifier or as a output. The number of states have been increased because of 2 reasons: conditional outputs have been removed and extra states have been introduced whenever 2 qualifiers are tested in series. And now we are not increasing the number of states as an example. I told you, so happens the previous ASM had 6 states. Now I have, you can see here, starting from 0, the highest number of states is 13, that means total of 14 states. 14 states requires 4 variables, state variables. Earlier ASM had 6 states, which required 3 variables, that means I am increasing 1 state variable. So, it is not going to be an enormous increase in size, whereas the number of qualifiers which is coming in the exponential power of the number of the size of the ROM, is now going to save this the reduced number of the size of the ROM that we require in this case. Now, with these values of state variables starting from 0, 1, I mean states addresses starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, total of 14 states. The qualifiers are start, TD, throw dice, dice greater than 9, greater than or equal to 9, dice less than or equal to 9, score less than 10, score less than 89. These are the qualifiers. Outputs are counter enable or count enable, add score, load score, enable number of attempts, enable the number of attempts counter, clear score, again load score, add score. S is the value which you have to give to either add or subtract a particular value to the score based on the game algorithm. So, these are all the same, no change has been made either in the symbol or the description of any signal. So, with this we will write the microprogrammed table for this implementation and see and compare the sizes. There are 6 qualifiers starting from 0 to 5, start is 0, TD 1, etc., etc. I have given the qualifier index 0 to 5. There are 8 outputs including no output case. So, I have given the codes for each one of them. No output is 0 code, load 2 is 1, counter enable 2, add score is 3, etc. You have two codes in which I have given 2 outputs. For example, LDS and enable number of attempts as a single output. The reason is LDS separately comes as a code 4, but then when I put a code 4 here, I will not get, I should not get these 2 together. Only one particular instance I should get these 2 together, rest of the time only LDS should come. That is why I have given a separate code for this. Likewise, we have S and adders, a separate code even though there is a code for adders. Now, this is the microprogram table. You just take one example, the present address 1, let us say, present address 1, qualifier tested is TD which is 1, true address is 3, false address is 2, there is no output here, that is why output is 0. So, present address 1, qualifier index is 1, true address is 3, false address is 3, false address is 2, output code is 0. That is it. Very simple. You can get the whole table done, go step by step, state by state, what is the qualifier to be tested, look at the qualifier index, put that value, look at the true value of the address, put the false value of the address, and then what is the output to be generated at that time. There is no output, you put a 0, otherwise give the appropriate code, and you got the table, and all you need is a ROM to program the whole thing. And I have already given the architecture of the microprogrammed ROM implementation in the last lecture using the simple example of a 4 state ASM. So, for this case, let us compare the size of the ROM, sizes of the ROM required for the conventional approach and the microprogrammed approach. In the conventional approach, now that we do not need this, I am going to remove sizes comparison, conventional, there were 6 states, as I said, you will have to verify, go back to your notes of the implementation of ASM for dice game in the earlier lectures. Number of states 6 qualifiers, 8 outputs, this is all same, you know. Now, size would be 2 power 6 states will require 3 state variables. So, 6 plus 3 9, ROM size would be 2 power 9 times the number of states 3 and output 8 11, or you want to code this output into 3 bits again, or 2 power 9 into 8, 2 power 9 into 6. That is, each 3 state variables and 6 qualifiers are the input address. So, you have 9 address lines, 2 power 9 is the size. Number of output lines are the state variables and the outputs. State variables are 3, outputs are 8, 11, or if you want to code the outputs into 3 bits, it is 6. Now, microprogrammed approach. Single qualifier, double address. How many states are there? 14 states, starting from 0 to 13, 14 states requires 4 state variables. Number of qualifiers is same. And number of outputs is same. It can be coded into 3 bits. So, size is now the state variable alone, the address alone. Address is the number of states alone, the number of bits in the address, I mean number of bits in the state. There is no need to give the qualifier as the address. So, the size would be 2 power 4 times, what is the qualifier index, how many bits? 3 bits, 2 address 4, false address 4, 4 plus 4 8 plus 3 11. I can have 8 of this or 3 of this depending on whether I code or not code. If I do not code, it will be 19. If I code, it is R 2 power 4 times, if I code it, it becomes 3 plus 4 plus 4 8 plus 3 11 plus 3 14. So, either 2 power 14, 2 power 4 by 14 or 2 power 4 times 9 bits, this is also bits, everything is a bit. So, in this case it is 2 power 9, 2 power 9 is what? 512. So, let us go to the, let us go with the coded output case. Let us go with the coded output. So, in the case of conventional ROM, it is 512 by 9 6 bits, conventional. Microprogram, it is 16 times 14. You decide which is bigger and how much, and that is only the size, and I am interested in elegance, elegant design. Design has to be elegant, easy to do it, and it should be a charm, nice. One minor modification at the end, and that would be to make it into a single qualifier, single address. design. The only requirement being one of the addresses should be an increment of the present address, other address can be anything, and that is also called a jump address, even though we call it true address or false address, because either you increment it by 1 or jump to a new location. So, some people call it jump address and some books call it jump address, anyway it does not matter. So, we need to give only one address called the jump address, which is a non-incremental value of the address. To that extent, I am going to make a modification in the ASM. I am going to make it and I am going to leave the rest to you. I am going to tell you where the modification needs to be done. It has to be done. They need an increase. You need a you need to increase. There is a need for an extra state here. I'll just show it here. I'll tell you why an extra state is required here, because this is 0, this is 1, that is fine. This is 12, this is going back to 12, and this is 1, I cannot have. So, one of them has to be, this is 0, this is 12. This state has to be next state of this as well as next state of this is impossible. It is not possible for this state to be next state of this as well as next state of this. If it is next state of this, it cannot be next state of this. If it is next state of, I can modify it and make this 12 and this 13, in that case this will not be next state of this. So, I need to have an extra state. So, this extra state is the only extra state required in this case, extra state, and then I need to make changes in the addressing. I will just quickly do it. I thought I will leave it to you, but then address will change like this. This 0 will remain 0, this will become 1, this 2, this will be 3, this will be 4, this will be 5, fine. This will become 5. This will become 6, will become now 11, this will become 12, this will become 13, this will become 14, this will become 9, this will become 6, this will become 7, it will become 8. So, I need to make two changes. One change, introduce an extra state for which the address will be 10, of course. I need to introduce an extra state with the address 10, and I need to make some changes in the addressing scheme. So, the new addressing scheme will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, one extra state and some changes in the address. I am not going to do the rest of the work. You do the table, present address, qualifier index, true or false bit, true bit to be 0 or 1, the jump address, the next address, the output code, and I can only give you the size comparison, size of double address, single qualifier, single address, microprogram ROM. Size would be, I want you to check it yourself, size will be 2 power 4 times 16. If you want to not, if you do not want to code it, the outputs are 2 power 4 into 11 bits. So, this, since you are only comparing the coded outputs, 2 power 4 11, so it is 16 by 11. This is double address, this is single address. So, conventional 512 by 6, double address microprogram 16 by 14, single address microprogram 16 to 11. So, you can also see the change in size. Earlier example of the simple example of 4 states, I could not show you the size improvement. Now I can show you the size improvement. That is a 64 bit saving in the size. and not much change in the state diagram, extra state and redo the addressing. So, this is a very nice thing, because in major digital designs, in a computer for example, a controller has so many functions, so many qualifiers, so many outputs. It is very difficult to keep track of a ROM where we will for each state we will write the inputs true or false. We always are local, we are concerned with the local state and this neighborhood. At this state what happens? This state what are the qualifier tested, where it goes, what is the output. So, that is the approach we are going to take. The design will be very efficient. So, the microprogram approach has very good potential in major digital design. Lot of people use it. Microprogram controllers are very common in microprocessors and so many other digital systems. Except of course, any program takes more time than a hardware. Hardware means already have everything connected. As soon as the system is turned on, its signal passes and you get the output. When microprogram, it takes time for you to go to the state after state after state. Except for the change in this speed, which is except very high speed, ultra speed designs, microprogrammed approach is a very practical and elegant option. We will stop here for this microprogram design. Thank you very much.